Hello, my name is Snigdha Sethuram. I'm working with Rachel Cochran and Chris Hayward on creating a radiative transfer emulator using an artificial neural network, which we have decided to call Angelina. And Gergo Popping and Li-Chen Liang provided the data sets that we trained our networks on. And Viviana and Paco provided a lot of insight for the machine learning aspects of our project, so huge shout out to them. But first, I want to talk about what exactly radiative transfer is. For those of you who attend the Galaxy Formation meetings, you already heard my opening spiel, so I'll keep it quick. Basically, the way light travels through space is extremely important in astrophysics, as I'm sure everyone knows. And the way it travels through space can tell us a lot about the composition of the space through which it travels. Radiative transfer is the process of tracking the scattering, emission, and absorption of light through dust and matter. And there are many things that affect the composition of photons, such as metallicity abundances, morphology, dust grain populations, re-emission from heated dust, etc. And radiative transfer will output an observable SED, or spectral energy distribution, which is the mapping of the flux or light emission intensity to different wavelengths. Shown on the left here is one such SED where we can see these flux values as a function of wavelength. And observers will automatically see this SED when they're observing. But in simulations, in order to be able to get the SED of a galaxy, you have to run post-processing RT code, radiative transfer code, on the simulation, which takes in three-dimensional particle distribution data and then outputs the SED information. Since the physics is so intricate and there tends to be many particles in a simulation, running RT code on them can be extremely computationally taxing. And running cosmological simulations themselves are already taxing, let alone running RT, which can cost a lot of time and money that groups don't have. So many people make educated assumptions about their simulations to assign observables to their galaxies, which introduces a lot of compounding errors, especially in an area where observers are already kind of iffy about trusting simulation data. And so we want to facilitate forward modeling or mapping simulations to observations to allow very direct comparisons between simulations and observations. Shown on the left here is a figure that Rachel made. Here are some global properties that are available within simulations. And then on the right are mock observations, which are made by getting the flux at different wavelengths from radiative transfer code. This is what an observer would see through an aperture of a telescope, which makes it possible to directly compare this simulation information to observational data. And that's why it's important to facilitate forward modeling by making it easier to obtain observables. And previous works by Safarzadeh and Hayward have shown that certain submillimeter flux values of obscured galaxies can actually be determined pretty close to accurately with just a few global properties like star formation rate and dust mass. And so we decided to expand upon this idea and create an emulator that could basically spit out the SED of a galaxy given its global properties, which are available in the simulation. Traditionally, radiative transfer takes the three-dimensional particle distribution data and then implements the chosen subgrid models to obtain an observable SED. We want to do this instead using a fully connected artificial neural network that is trained using existing SCIRT radiative transfer outputs of Firebox and Illustrious Team G50 datasets. SCIRT is an eminent and robust radiative transfer code written by Kamps and Baez. And as shown here in the workflow, we basically want to replace the post-processing RT step with a less computationally expensive neural network. So instead of giving it the full 3D particle distribution data as input, we only want to give the model global properties and then see if it can learn the relationships between these global properties and the resultant SED while blind to the particle distribution. Our wavelength range of interest spans from the far UV to the far IR, so from 0.1 to 1000 microns. And we're hoping that groups will be able to apply a successful model to as many simulations as possible. But one of the primary goals of this project is to be able to apply a successful working model on the CAMELS database. Since the ISM is not resolved in those simulations, which affects the performance of RT code and can provide or can create very unphysical results. The database is also huge, and so it would be infeasible to run RT on even a small subset of the simulations. And so implementing a working model on the database would be a huge plus. In addition to any groups that use semi-analytic models, which lack particle distribution data, if we are able to create a model that can give you an SED with just global properties, which semi-analytic models do have, then that would also be useful to groups that use those simulations. So a little bit about the data sets. Both Firebox and TNG50 have complementary characteristics. TNG50 has a larger number of more massive and luminous galaxies than Firebox, but it's not as highly resolved. While there is AGN feedback modeled. Whereas in Firebox, there is no AGN feedback modeled. It has a smaller box length, and so less massive halos and a fewer number of galaxies, but the ISM is resolved. And again, there's no AGN feedback. I think I already said that. There are differences in the subgrid models or subgrid physics used as well in the simulations, as well as in the skirt radiative transfer codes. And so when we attempt to test the robustness of our model, we'll be able to determine whether it's learning the subgrid relationships in detail or if it's able to understand the flux to wavelength mapping in a more general sense, in which case it would be applicable to a wider range of simulations. But moving on, let me give you a little rundown of Angelina. So we trained a separate neural network for each data set and then used Optuna, which is a neural network parameter tuning package, to tune the hyperparameters and determine the most accurate model possible for each data set. After several interpretation steps, we are tentatively firm that using SFR, dust mass, stellar metallicity, young stellar metallicity are good features to predict the best SED with the most minimal number of input features. So our input layer is the global properties layer. And then we have between 2 and 3 hidden layers for all of our models, which is why we stopped calling it a deep neural network and instead are sticking with ANN, which is very conducive for our moniker. And then our output layer is the resultant SED for each galaxy. And the size of the SE or the size of the output layer is going to be equivalent to the size of the wavelength array for the data sets, which for Firebox has 250 wavelengths and for TNG50 has 200. As I mentioned, we're currently cross-testing our models to test how robust they are to different subgrid physics, for which we have some preliminary results, but it's ongoing. And once we complete testing to a satisfactory degree, we're going to release the methodology for the model as well as a GitHub repository so that any groups that want to create a model like this for themselves with their own data sets or different types of simulations will be able to use these starter scripts and build it easily. So to train our models, we used an MSE loss function, the general definition of which is shown here. But while testing, I calculated the MSE of each test galaxy to see how the models were performing on a case-by-case basis. And so since the SEDs logged going into the model, when I calculate the MSE for the test set, essentially the MSE function becomes the mean of the log predicted SED over the true SED squared. And those are the values plotted here for all of the halos in the test sets for both Fire and TNG. As you can see, the Firebox data peaks at a higher MSE bin than TNG50, and the distribution of it is wider as well. The average MSE for Firebox is 0.06 and for TNG is 0.01. So just in general, the TNG model is performing slightly better, for which we generally think that it's because, first of all, our TNG data set has more than double the number of data points. And also since the output layer is smaller and we're going from a very small input layer to a very large output layer, the larger the output layer is, the higher our error is going to be. We are including weight decay and dropout, especially due to the small size of our data sets and the interpolation from a small feature set to a large output layer. We want to avoid overfitting as much as possible. So we have pretty high values for those. And then here's the good stuff. Here are a couple fits of TNG. The blue line plotted on top is the skirt true SED, And then plotted in red is the neural network estimate of the SED. And as you can see, it's doing pretty well. And on the bottom, the fractional difference is plotted, basically just the predicted value minus the true value. Sorry, it's jumping. And so again, since the SED is going in logged, it just becomes the log of predicted over true, which is telling us the DEX difference between the skirt and the neural network model. And then in this one, you can see that in the UV emission, the error is much higher than in the IR, which follows some of our physical intuition because dust is transparent or mostly transparent to IR wavelengths, but UV is very geometry dependent, and we are not including any geometry inputs as of right now. And so we expected that since the model is not being given any information about the geometry of our galaxies, it would generally perform worse in the UV than the IR. So it is a little bit comforting to know that the model is working as expected. Here are some firebox fits as well. Again, the top, the skirt, and the neural network, and then the fractional difference on the bottom. And again, you can see that the UV error can be higher than the IR. And again, this is one where the UV is very obviously a higher error. Oh. All right, so let me just explain what's going on here for a second. This plot on the right just shows one SED with the color coding corresponding to the color coding of this plot right here. These plots are showing the maximum fractional difference, so the maximum deviation from 0 in this plot. Up here is showing the maximum fractional difference across the whole SED. So the maximum deviation at any wavelength is plotted here for the test set of TNG. And then down here, it's separated into the maximum fractional difference per wavelength band, again, which is color coded over here. The black line here is the UV, and you can see that it's performing much worse than all of the other wavelengths, and in general is driving the maximum fractional difference of the whole SED. But we are able to predict a majority of our halos to within a factor of about 2, which is pretty promising, especially in TNG. And all of our, in TNG, all of the errors peak in the lowest fractional difference bin. And then here's the same plot for fire. Again, the UV is driving this low maximum fractional difference across the whole SED, but the IR is doing very well. And again, this is as expected. So some things that are going on right now, we're still cross-testing. Once we determine whether or not these models are robust to subgrid physics, if they are, then we will be able to combine the two data sets together to create a combined data set model, which can expand our input parameter domain. We're also thinking about creating a separate neural network for the different wavelength bands and then combining them to create the SED output, which may learn the correlations between the SED at wavelengths close to each other better than this model that's trained on the whole SED. We also are considering putting in geometry as an input, inclination angle, axis ratio, et cetera, just to see if that improves the UV emission. And then finally, Viviana is doing some PCA testing with our data set, and we have some preliminary results there as well. So we're looking into testing that further and potentially incorporating PCA testing into our model, either in parallel or as an additional interpretation step. So everything is still a work in progress, but we have some promising results so far, and I am open to questions.
Thank you very much, Snigdha. You're perfectly on time, so that's much appreciated and really really nice talk. My unbiased views. It's great work, of course. So now we have time for any questions. Quang.
Can you hear me? Is this?
Yeah.
Yeah.
Okay, awesome. That's really awesome work, Snigdha. I was actually really curious as to the fractional difference plots. Is there any expectation that structures in this like fractional difference line correlate to physical interpretations, or is it just random noise?
So some things such as this peak do correspond to certain Or do you mean like in the fractional difference line or the SED model?
The fractional difference line, like, are you?
I would say, I think no, like some parts like this do correspond to certain features in the SED, but in general, we don't see many trends in the shape of the fractional difference across the SED. Was that your question?
Shai? Oh, sorry.
Sorry, was that your question?
Yeah, that was it. Thank you very much.
Okay, cool.
Go ahead, please, Shai.
Thanks. Yeah, really beautiful results. I'm curious about the orientation thing. So have you fed the RT calculations themselves were done from different lines of sight for a different line, like a random line of sight for each galaxy, or what?
So I believe the calculations were done from a different line of sight, but all of the training data that we have are the simulations have been rotated to match the angular momentum. So it's based on projections that we're training on. So we would need, if we are including geometry as an input, especially if we want axis ratio as an input, we would want more data sets with multiple angles.
Yeah. Okay, because yeah, I was wondering if the network, even if you don't give it the geometry or the line of sight, if it would still be able to somehow learn the distribution, the different ways each galaxy can be seen from different lines of sight, if the training set included like random lines of sight for different galaxies. So that's something you could maybe test by providing extracting different predictions from the neural net for the same galaxy by different initialization of the neural net, for example, and see if the distribution you get matches the distribution from the RT calculations.
Definitely. That would be a useful test.
And we'll take a final question from Julianne.
Yeah, my question is kind of in the same angle as Shai, and that it might be interesting to look at just there's probably some intrinsic limit about how well stuff can do given geometry, right? That there's the UV is going to change depending on viewing angle, and for the parameters that were on the left side of your neural net, the exact same galaxy viewed in different ways could have different answers. So it might be nice to just sort of know, like, maybe you don't have to work to make something better because that's just as good as nature will let you have it.
Yeah, definitely.
Yeah, my name is Ankansur. I first would like to thank everyone for giving me this opportunity to be in this Pre Doc program. This has literally been the best 5 months during my PhD. So the title of my talk is Radio Polarization of Millisecond Pulsars with Multipolar Magnetic Field. And my supervisors were Dr. Yachi Yuan and Dr. Sasha Filipov. To give you some context, we are interested in millisecond pulsars, which are rapidly rotating neutron stars having a spin period of less than 10 milliseconds. And these objects emit jets of charged particles above the magnetic poles, which are then accelerated and emit radio waves. So these beams of radiation sweep around like a lighthouse as the star rotates. And on Earth, we observe these pulses of radiation, which are so precise that this can be compared to atomic clocks. However, the coherent emission of radio waves, these beams still remain theoretically unclear. The magnetic field of pulsars plays a very important role in their lifetime in driving many physical processes. Therefore, we must understand what kind of magnetic fields exist. So in ordinary pulsars, we have almost dipolar magnetic field, not only assumed for, reasons for simple, because it's a simple model, but also inferred from spin down of pulsars. However, recent observations by NICER satellite have shown that studying X-rays were able to locate the hotspots on the neutron star surface, which are regions of open field lines, and which shows evidence of multipolar magnetic field. Moreover, dipolar fields are unable to explain sufficient pair production required for this pulsar emission, because these have much shorter curvature radius of curvature. Now, one of the key methods to connect the surface magnetic field to observations is polarization modeling. The pioneering theory in this field is the rotating vector model proposed in 1969, which predicts the position angle using the projection of the magnetic field onto the sky plane. Therefore, tan of this position angle psi is given by the ratio of the magnetic field along the y-axis divided by the ratio of the magnetic field along the x-axis. And this model assumes dipolar magnetic field. So if we look at this picture, the angle alpha is the angle which the magnetic moment axis makes with respect to the observer, which is along the z-axis. And the angle delta is the angle between the observer and the rotation axis. Now, given a magnetic field at the emission point, the magnetic field is oriented along the observer's line of sight, and this determines the direction of the emission. And the trajectory of a ray propagating in this direction is given by the location of this position vector REM, emission vector REM, plus a height which this ray travels before the polarization freezes. So this height, which we call h, is the freezing height. Now, this is the line of sight of the observer, which lies in this emission cone, making a small angle with respect to the magnetic moment axis. And as the star rotates, the poles move along this circle. And as the star rotates, the line of sight cuts across the magnetic poles, and the plane of linear polarization sweeps a characteristic S-shaped swing over a single pulse period. So this is theoretically predicted. Now, if we look at observations for ordinary pulsars, indeed, we recovered this S-shaped curve of the position angle. However, this is very much different for millisecond pulsars, which show flat or even random, distorted or even random position angle curves. So the question that we are interested in is that how to reproduce the polarization of millisecond pulsars. Before going into this, we must understand what type of the magnetic field or what the geometry of the magnetic field of pulsars. So for the millisecond pulsar PSR J0030, which is the nicer pulsar, we consider a vacuum multipolar field where this dipole moment parameters is given by this, and this is located in the YZ plane. And the quadrupole, we also consider a quadrupolar field given by these parameters. So the overall effect is that we have this quadradipolar field. And we use them to evolve using the force-free simulations until and unless it reaches a steady state. So in the steady state, we see that this quadrupolar field, which are these loops in this middle picture, lies close to the surface of the star, and far away from the star, we have more the dipolar components, as seen by the right-hand side of the picture, which are far away from the star. Now, this field was able to simultaneously produce the light curves of PSR J0030 in gamma rays, in radio waves, and in X-rays. Now, before we calculate the position angle curves, we are interested in, we first calculate the sky maps. So the idea is that along in this emission sphere, we move the observer at each point, and at each point we have this direction of emission. So we map each point on this emission sphere to an observer plane and calculate the polarization. And the emission is subject to this subjected to this time delay, which comes along this term on which is E dot R terms, given that the ray propagates for a finite distance. So this is the sky map of polarization. And if we fix a viewing angle, we can recover the polarization curve. So for the dipolar field, we calculate the position angle curves for different, by varying the different parameters. For example, this is the effect of freezing height. So we see that as we increase the height of, as we increase this height h, the S-shaped curves become more more flat towards the more vertical. Similarly, we also can vary the emission radius, and this also affects the S-shaped curves, and similarly the viewing angle. However, as this pulsar is surrounded by a plasma, and this plasma is co-rotating, we are interested in the effect of aberration because it's also rotating faster. So the new emission direction is not only given by the magnetic field, but it's given by this velocity where an additional term of omega cross r enters. And the polarization is then calculated using the wave field in the co-rotating frame and then transferred back to the lab frame. So we get these additional terms. Now, instead of this by over bx, we have these additional terms corresponding to beta, which is this omega cross r vector. And the effect is that the aberration makes this S-shaped curve move towards the right hand, moves towards right. Similarly, we do the same exercise for the quadra-dipolar field. This is the vacuum solution, and we get a messy feature, which is also seen in the position angle curves. However, the good thing is that if we increase either the height of, either the freezing height or the emission radius, we recover this S-shaped feature, which is expected because far away from the star, the field is more dipolar. In reality, we are interested in the force-free field because this is what was used to reproduce the light curves. And we also consider emission from the open field lines. So on the right-hand side, we plot the regions of these open field lines on the emission sphere. So at r em equal to 2r, which is the surface of the star, we get this arc-like, one of the poles is this arc-like shaped and the other pole is more circular. And as you increase further, these regions become larger and becomes more oval. So this basically tells something about the geometry of the magnetic field. And similarly, we produce the sky maps from these open field lines. And if we fix the emission radius at 3r, we vary the height of this emission, we get that at very close to the surface, it gives this flat feature. However, at a very higher freezing height, we get more like an S-shaped curve. And similarly, we can vary the radius of emission, but fix the freezing height. And in this regard also, we see that far away from the star, this is more S-like. So ultimately, what we directly want to compare is observations of this pulsar J0030, the position angles, which is so these are the two observations. One is at a frequency of 1.4 gigahertz, and another is at around 400 megahertz. So there are these two shapes coming from the two different poles. So we believe that the first one is more like an S-shaped curve. So it's coming from far away from the star. Whereas this shape at over here is coming from at REM equal to 3R. Moreover, for this, at this frequency, we are trying to reproduce what happens to this position angle over here. And we get that, we recover that at REM equal to 5R, this more or less looks the same. So in summary, I would say that polarization model is important to constrain the magnetic field geometry. So we have calculated the position angle curves for this pulsar, given that we do not know this emission radius, but we can vary the emission radius and the freezing height and directly compare with the observation. So we can constrain from where this emission is coming from. We have included the effect of aberration, and this is particularly important for millisecond pulsars because these are rapidly rotating, and this omega cross R terms becomes important. And our calculations are the first, and it's kind of more meaningful as compared to the previous literature. So we do not include any propagation effects yet. And our pipeline can be found at my GitHub called Millisecond Pulsar. So thank you very much.
Thank you very much, Ankan, for the great talk. And thank you to you also for being right on time. Now we have some time for some questions. Bart?
Hey, Ankan, great, great talk. I really enjoyed it, and nice results. I was wondering, like, if you take a next step with this work, what would be like the next type of realism you would add to your simulations? Would there, like, would you add accretion onto a millisecond pulsar with MHD, or would you look into like particle and cell simulations to look really at maybe radiative effects? Can you give like an insight on what you want to do next?
So far, I mean, we are still yet to constrain this emission radius and height in order to exactly reproduce the observations. So far we are, I mean, this multipolar force-free solution looks great. So there have been some intuition that we are using this at a time where there might be current sheets which are more turbulent, and therefore we might want to use a data set at a previous time where, I mean, yeah, I mean, we don't have more plans of doing simulations or including any radiation effect. I think this piece of, I mean, if we are just able to reproduce from first basic principles just to using this multipolar magnetic field to reproduce the observation, I think this is kind of a pretty good result.
Great, thanks.
Deborah?
Yeah, I wanted to ask, your last slide says no propagation effects yet. With my pulsar timing array hat on, I wanted to ask, does that mean there's pulsar timing or propagation effects in the future?
Yeah, so that's a call we have to make, and I'm not sure how important are propagation effects. Yes, of course, we can vary the density of the plasma and things like this. Maybe it may be important for if you want to model the circular polarization. So
yeah, I would say, you know, I think propagation effects are pretty important. They matter a lot in getting your sort of best possible timing model, but obviously there's a million things you could try, including a bunch more pulsars or any number of different directions. So this is really cool work. Thanks.
Right.
Jonas?
Hi, Anka. Great results and very interesting. So
Thanks.
I think, could I conclude from this also from physics of pair cascades that now you can basically start to be able to constrain the height of a location of the pair cascades where they happen, and this would really point out that millisecond pulsars maybe even have the pair cascades happening closer to the star than the normal, basically in order to probe the messy quadrupole or multipole field structures.
So I mean, what we see is that these I mean, in order to reproduce this at observation at 440 megahertz, I mean, this is pretty close to the surface of the star, so we should be able to constrain this emission height of these pulsars. But it does depend on the magnetic field geometry, so there may be other magnetic field geometry also explaining the observations. But at least we can constrain with our models.
Thank you. That is extremely cool. Thanks.
The title of my work is a joint probabilistic model for spectroscopic eclipsing binaries, or as I've discovered, putting 2-minute cadences and 2-day cadences together. My primary managers are Dr. Dan Foreman-Mackey and Adrian Price-Wellen, but I've also collaborated with Trevor David for a lot of advice on modeling eclipsing binaries. And so to get to the main matter, being astronomers, we all know binaries matter, but just to make sure we're all on the same page, binaries are one of the most robust ways of deriving a star's mass. They don't require any models and are very relaxed in terms of needing calibration. In addition to that, they're also one of the bottom rungs of the cosmic ladder, and eclipsing binaries have even been used at this point for extragalactic distances. In addition to that, they're also useful for Hertzsprung-Russell diagram calibrations, both in the population sense in star clusters, as well as individual stellar models. And because of the large catalogs now available, such as Apogee and TESS, we can now put together the transit and RV data across the entire sky, offering conclusions that can be drawn for the entire Milky Way at this point. So the work I've been doing focuses primarily on using TESS data and Apogee data, as I said. TESS is a transiting exoplanet satellite that has been going since 2018 and is observing over 85% of the sky and has 2-minute cadences for over 200,000 stars. Apogee, which provides spectrographic data, actually wasn't originally commissioned for time series data. It was originally commissioned for chemical analysis in the Milky Way with multiple observations per star that could then be added together. But people found that the RV variations lent themselves really well to binary studies. And so that has been a fruitful side product as well. It's been operating since 2011 and is currently in the 17th data release, which we use here. And they now have over 650,000 stars and over 2.5 million visits for that group of stars. So it's really good coverage. So to start our model, we wanted to have a small group of systems that we could really experiment and go into the weeds in the model for. And so we looked to the Joker pipeline, which was a radial velocity only binary modeling pipeline developed by Adrian Price-Wellen. And so the gold sample of that model had 2,600 systems with more than 3 RV measurements. We looked at the short period binaries, less than 10 days, because that ensured that most of the eccentricities will be close to 0, and the circular binaries will be easier to begin the model with. And that brought it down to around 1,700 systems. We then cross-matched this with the TESS input catalog and found that there were 60 systems that had short cadence light curves already processed by the SPOC group. And so that made it easy to just plot all 60 or so of these systems and run a Boxley squares algorithm on the light curve to look for any interesting transits. which brought it down to a very manageable 13 systems. And so here we have the 13 systems plotted with the tick ID present at the top. The x-axis is the folded phase of the period according to the VLS, and the y-axis is the part per thousand normalized flux. And so all of the light curves are colored by their observations using the plasma color table. And so, for example, in the top left plot, you can see that there's only yellow and black present. That's because this system was observed with a 2-year gap in between the consecutive observations. And so the systems where you see a clear gradient from gold to purple, those have much more consecutive periods of observation, whereas the gold and black ones have large gaps. So there's a variety of different observational cadences used. And so the cyan line is actually a binned histogram of the flux as a function of time. And you can really see how the trends stand out when you bin it this way, even for the more noisier light curves. And so to model the orbital, these eclipsing binaries, we used PyMC3, which is a robust Bayesian sampling software that lets you run Python code and then almost just translates it to STAN, which is another sampling code. But we decided to build our model using physical binary parameters, such as the mass and radius of the primary star, and then little k, which is the radius ratio of the two stars, q for the mass ratio, and s for the brightness ratio of the two stars. We also modeled the eccentricity using a unit disk function. We also model the binaries using the observational parameters, such as the impact parameter, which is a way of describing how close together along our reference plane the two stars come in front of each other during an eclipse. T0, the epoch of the first transit, and then Tn, which is the time of epoch for the nth transit in the light curve, as well as the argument of periastron omega, which we also derive from a unit disk function. We include noise parameters for a background RV and a background light curve, and we subtract the light curve background using a Gaussian process, which is modeled using a stochastic harmonic oscillator. And then for the radial velocities, we model a sigma RV for the apogee measurements. The model is put together with these variables, and then we calculate the likelihood against the joint data from TESS and apogee. And so this is just a simple illustration to show how the Gaussian process works to help the model fit the light curve. And so here we have a very short period eclipsing binary 2021-5452. This is the unfolded light curve, and you can see the initial transit model is overlaid in cyan with the Gaussian process in gold. And so when we fold it together, we have these really exquisite phase variations in the folded light curve, which the GP is able to pick up on and then also model it out so that when we fit the model to it, we get a very clean fit without worrying about any issues. Of course, this does mean that any interesting binary information contained in the phase curve itself isn't something we're actually looking at. We're more primarily focused right now on just binary orbital parameters. And so before we actually start the model, we also want to initiate it with a better test point than simply doing order of magnitude calculations. And so for that matter, we use the isochrones Python package, which fits photometry using isochrones developed by the MESA stellar code group. And so we have individual observations for each system, and we apply an unresolved binary model fitting to the Gaia photometry as well as the J, H, and K photometry. This allows us to catch any infrared information that the secondary may have, which is typically not picked up in Gaia photometry. To help with distances, we also use the EDR3 parallax. And then we also use the apogee T effective and log G estimates just to help the model, this initial model, converge more rapidly by narrowing the age range. And then with the fit results, we calculate the estimates for the mass the primary mass, the primary radius, and the K, Q, and S ratios. We did experiment as well with a fudge factor on the standard deviations of these values, multiplying them by a factor of 1, 2, 4, and 8. And then we also organized the map optimization steps of the orbital parameters to make sure that the log probability is maximized without letting any one parameter be set in stone. And so from this, we end up with those 13 systems that I showed before. We found that a fudge factor of 8 works best. This kind of indicates that the isochrones package may be a little bit biased, and later on we may actually use it to calibrate the isochrones model better. But we have 10 completed model runs for our 13 systems. 7 end up having really good models based on the light curve and radial velocity curves. 3 of them were very poorly modeled, and this isn't because of low number of RV measurements. Some of them have over 15. It's just an issue with how the Gaussian process is handling different phase curves. 3 of them never made it because the optimization failed and the model crashed, which is something we need to look at in the future. Here are the 7 systems that had good fits. Something I really want to point out is that all of these orange model curves have confidence intervals plotted, both 1 and 3 sigma, which means when you see a straight line, that's how tight the posteriors are from the finished samples. And you can see, for example, in the 3rd column, the light curve has some clear confidence intervals, whereas in other systems, it's an extremely sharp line. So the model was really able to derive orbital parameters well when combining both sets of data. And also, this doesn't require any fine tuning on our part. We only have to give the pipeline the tick ID to download, process, and then run the model sampling. And so next, we wanted to compare these 7 models with the literature. We used the Torres 2010 catalog of eclipsing binary parameters. And so here we have the mass radius plot, which almost follows the main sequence structure. And we can see that we're kind of pushing towards the lower end of mass as well as radius. And here we see that we're not, as expected, we're doing very short period binaries. So naturally our eccentricities are all very low. However, we do still cover a wide range of semi-major axis over primary radius values, almost falling in line with the Torres 2010 catalog. And then here we plot the A over R1 value of each binary against the period normalized by something called P surface, which is meant to remove a dependency between the binary period and the surface gravity and radius of the primary star. And you can see really well that our systems fall well into line with the Torres 2010 catalog. And so after this, the next steps are to just expand the model to handle more eccentric systems. Right now, we're kind of taking it easy with just doing primarily circular systems. Also increase the periods where this gives us access to a larger array of binaries, possibly even 30 to 50 systems. And then also as well, possibly considering more evolved systems, which may even let us develop a group of benchmark binary models that can cover the entire HRD so that we can calibrate more precisely, as well as also consider whether or not we can give the model less than 6 visits of RV data and still find a good fit to happen. Also, right now, the model is assuming 2 eclipse transits in the light curve. We need to see whether or not it's possible to have the model accept that in a particular system, there may only be the primary eclipse and no secondary. And so in conclusions, we found that we were able to generalize a binary model with apogee and test data. And again, only requires a tick ID the way the pipeline is implemented at this point. We get 7 out of 13 binaries modeled, which we think is pretty good. Only 3 model crashes, which is nice. And then the fact that we were able to implement initial test points with the isochrones package was really encouraging. However, we do find that the models are a little bit too bias. So we need to smear out those standard deviations by a factor of 8 in order to get the best results. And currently we're working on a paper to introduce this method before we move on to considering the benchmark catalog. And so I guess I'll take your questions now, and I'll leave you with an animation of the 7 binaries.
Thank you very much for the great talk, Carl. The cat was very popular on the chat, so we may have some questions about the cat or other things. So open for questions now.
Hi, that was really nice. Can you go back to the mass radius plot for a sec?
Sure.
Yeah. I mean, first of all, I just wanted to stare at it a little more.
Oh, sorry.
But I guess I kind of have 2 questions. One is like for this sample or Apogee more generally, what is this a region of the mass radius plane which is well known, or is this adding, you know, sort of information to what's known in the literature? Because there aren't too many points on this plot if you just included everything we know. So that's kind of one question I don't know the answer to. And the other one is like, what would be the best, like these error bars are still pretty large, I guess. I'm not really sure whether they're 1 sigma or 2 sigma, but I guess what would be the most important information to narrow those? Do you just need like dedicated RV on these particular systems or something else?
So these are I believe 95% confidence intervals on the mass and radius. I plotted it this way so that we can see the covariances between the radius and mass of each of the systems. You're right, this isn't a lot of points plotted as far as the literature is concerned. It's only this Torres 22 catalog. And really you can still see some of the Torres points extend in the region that our sample is lying in. The point, however, is that this group of 7 only required 1 generalized model to get these results, whereas other literature groups or other papers have looked at combining both light curve and apogee or RV data in general, but those require or have typically been done by very boutique models that aren't applicable across binaries. So it's more so the idea that you can just give this model structure a list of IDs and it'll spit out these results.
Nice job, Carl. I just wanted to check to see if you had some intuition about the 3 crashes. Were there similarities between the objects, the data, etc.?
So in those cases, we, from what I've been looking at the post-processing before the model crashed, it seems in a lot of those cases, the model doesn't like having a non-existent transit being considered in the model right now. So those systems have a very faint secondary transit, which when plotted on a light curve on its own, you can kind of see it, but I think at some point with the Gaussian process, it may get subtracted out completely. And when it comes to the optimizations, the model just, the math, it doesn't like that. And so I get basically a linear algebra error that crashes.
Hi, Carl. I was wondering, what do you think are the prospects or limitations in terms of like scaling this up? Is it that like all the data exists, it just is the time to turn the crank, or is it that you need higher quality data, or you need to change the parameters? Like, this is incredibly interesting and promising, and it's like, what do you think is the future path?
So right now, we're working on simply getting a larger sample of binaries that have data across both Apogee and the test catalogs. And right now, as it stands, if we go up to higher period systems, that expands our sample to almost 50 systems. And so each model will only run for one system. So it's as simple as submitting, 50 jobs on Rusty to get results, but then it's just a matter of ensuring that the model can handle that much variation across systems, whether or not they're more eccentric, it's an evolved eclipsing binary, or non-existent secondary transit.
My name is Sofia Sanchez Mayes, and I am pursuing my astrophysics PhD at Harvard University. I've been a pre-doc for the last 5 months, and it's great to finally see what everyone else has been up to this whole time right now at the buzzer. So in that spirit, I am here to explain the few projects that I've been spending time on here with my mentors, Sasha Filipov and Bart Raperda. And yeah, let's get started. My projects both relate to the transport of magnetic flux within black hole accretion disks that I simulate. And this is important for many reasons, but just to kind of put those in context, I want to start with the basics, which is that black holes aren't really all that, black. We think of them as things from which light cannot escape, which is true in if there's nothing else going on, but black holes are systems, and the accretion power that they have generates jets, generates a lot of thermal luminosity. And so some of the farthest, most powerful, brightest engines that we see in the universe are, of course, black holes. Understanding how this really bright, really coherent emission ends up occurring is what I focus on in my work. And so to kind of give you a bit of context, I just wanted to brief on the basic anatomy of a black hole. Of course, black holes themselves are maybe a bit boring, just having a mass and a spin and a charge. Like, what do you even do with that? The really exciting part comes when you think about all the properties that you can think about with the accretion disk itself. So of course, the accreting matter has to kind of come from a place of a really high potential to a low potential to kind of fall into this gravitational well. And all of that energy goes somewhere. You can imagine that that explains all of this really bright, really powerful emission that we're getting. But in some cases, we need to invoke even more than this. And so a lot of folks have been thinking about mechanisms by which you can spin down the black hole and kind of take energy from that process by coupling the accretion disk of all of this, ionized plasma to the black hole somehow. And the result of all this work, was this thing called the magnetically arrested disk. Now, since I've been talking and will talk about magnetic fields, I want to point out that there's one property that black holes don't have, and that's a magnetic field. There are no magnetic monopoles, and black holes can't accrete magnetic field because the magnetic field kind of has to be embedded on something. It's all kind of connected to the matter it's around. And so we can think of black hole magnetic field as this matter is being accreted and its magnetic fields with it. The matter can go in, but the magnetic fields cannot. And so instead of having a picture like the left, we end up with something like the right. And I will, fully admit that I got this picture from, I think, a superconductor presentation or something, where like they were, same principle, very different system, of course. So just to give you a bit of a signpost for the geometries that we're going to be looking at today, here is our beautiful accretion disk of ionized plasma with some really powerful jet coming out of it. And you can imagine that you cut this in half and you think of the disk as like a donut of sorts. Then some of the plots I'm going to be showing you are kind of that cross section in between, where you'll see kind of two planes of the accretion disk with like a jet in between. So that's kind of like a vertical cut through, just to give you some orientation. So I guess all this begins here. This is supposed to be video, and I even made sure that it played earlier. This is disappointing, y'all. Okay, so anyway, I have these accretion disk simulations that I cook up, And there's one property that we see in a lot of these, which is that if we want to have very powerful, very efficient jet production, you initialize your disk with a very strong poloidal magnetic field. Where poloidal field, kind of think of the field around a bar magnet with, you know, that dipole. It's kind of vertically oriented. It's got some large scale coherent structure. And if we have that as like a precondition, then we've been able to generate jets and simulations for a very long time. And that's very nice. But the problem is that we have to invoke this field, this poloidal, strong, coherent field, kind of out of the blue. We kind of sometimes say that it's brought in with the disk, perhaps. But it takes a bit of imagination and acceptance to see how that happens. The magnetically arrested disk is the consequence of bringing in magnetic field with your flow that kind of, embeds itself very near to the black hole. It can't go in, of course. This simulation is from a neutron star, so the boundary condition is somewhat different. But I liked how it was able to show the property of the mad flow wherein, in order to accrete, material has to undergo a really Taylor instability or another instability to kind of weave its way inside of these very strong poloidal magnetic field lines that act in opposition to the gravity that's pulling in matter. So gravity wants to pull this matter in, but as all of this magnetic field starts building up outside the black hole, because it can't go in, that builds up a magnetic pressure that acts in the opposite direction and prevents accretion from occurring. So that, just wanted to show you in like a brief sketch this morning, what that kind of looks like is as you build up your magnetic field, your accretion rate m dot, it just goes down and down and down into some like pretty stable level. And as, that field builds up on the horizon, you have your magnetic flux accretion rate that attains some limiting value where it kind of stays in that stable condition. Now, this is all very nice because it turns out that since MAD is so good at making jets, we can imagine that lots of black holes could be something like MAD most of the time. But they're not MAD all of the time, and we still have the problem about where we got the poloidal magnetic field in the first place. So I think this gets us to the genesis of my project. I guess the inspiration came a few years ago when Matthew Liska, my collaborator at Harvard, ran this paper in the simulation where he started a simulation with no poloidal magnetic field whatsoever. At the very start, you can see we have only toroidal field, but then, already here, we already see some poloidal field lines. We're in a poloidal cut. If you see these solid lines, those are poloidal field. The dotted lines are also poloidal field, but kind of anti-lined to the solid lines. And just so you don't miss it, you see once accretion starts, you quickly begin building this poloidal field from your initially toroidal one. And you build poloidal field in both kind of alignments, both aligned and anti-aligned, if you will. And you can see that one of them happens to kind of stick and embed itself very near to the black hole. And that one seems to grow very much faster and very, very quickly and suddenly and powerfully and coherently to create the really strong, coherent poloidal field loops that are characteristic of a MAD disk, the ones that we always assume without necessarily showing what they come from, which is kind of a demonstration that maybe it could be done by the disk itself, by a natural process. And we can be really happy about that because the toroidal field that this simulation is started with, we almost get as a free present by virtue of the disk having differential rotation, which will shear out, which will always kind of amplify field toroidally. So that's really awesome. And we end up getting into a MAD flow situation, which is really great. So there were a few things about the simulation that were maybe a bit charitable to the cause of making a very powerful poloidal field. One of which is that all of these simulations that we run in our field about these accretion disks start with the configuration that is not in equilibrium. That's not our fault most of the time. Honestly, because of the complexity of the problem, there exist only a few equilibrium disk configurations at all. And there are no three-dimensional equilibrium conditions that have both poloidal and toroidal field. But in this very, very special case of a simulation, there is one equilibrium condition called the commissor of torus. And so one of the things that I was set upon doing and succeeded in implementing while I was here is being able to code up a commissar of torus, which has an equilibrium toroidal field only 3D configuration, so that I know it's not due to the geometry of the thing that you have this effect. So that was one of the things that I wanted to probe here. My impetus in all of this is to understand, we're getting colloidal field, but how exactly? The temptation is to say, well, maybe it's a dynamo. That's how we generate field here on Earth. We know very well this kind of like archetypal alpha omega dynamo, where omega, of course, is rotation usually, and differential rotation here, that's twisting field lines into toroidal and amplifying them in that direction. And the alpha effect, it looks like a little twist tie, a little twist, is when these field lines inevitably have some like buoyancy and stability or something, and they twist out because the fluid has shear, then you end up creating colloidal field once again. This is kind of the harder step of the two. Omega is kind of for free, and alpha takes a bit of imagination. So in order to see what it is exactly that's producing colloidal field in the simulation, there were a few things that I wanted to check. So of course, one of the things that I thought was interesting about our simulation is compared to like other normal dynamo simulations is the fact that in a black hole system, not only do you have differential rotation, but once you get very close to the central object, you also have kind of a space-time shear where the spinning black hole kind of takes the adjacent space-time with it for the ride. As you can see in this little Wikimedia Commons simulation of the locally non-rotating little probe thingies. And that's super cool because maybe that could really be the thing that's amplifying it so suddenly when it lucks out and gets very near to the black hole. So that's something we wanted to look into. But the things that I was actually modifying in the simulations that I was able to run were the initial magnetic vector potential by implementing the commissar of torus instead of just doing a Fishburne-Moncrief like typical. I modified the plasma beta in the simulations. What is plasma beta? It's the ratio of magnetic pressure of the plasma pressure to the magnetic pressure. And so modifying plasma beta means I'm kind of modifying the level of the toroidal field here. I changed the resolution of the simulations within these various runs, which means that I'm really changing the amount of numerical and actual diffusion that's present in this simulation. And I also ran some where I have a shorter disk. The last thing that I was able to change, which kind of modulated on these initial simulation conditions that were maybe generous, was the noise perturbation initially, which was at a very high percentage in the Liska run, and which works just as well at very low percentages in mine. And so a lot of my initial time here at the Flatiron was spent kind of setting up all of these different physics so that I can do these simulations and getting them going. And once I could press run and let them be, I was able to work with Sasha on a second project, which I will only just be able to introduce, which is more analysis focused so that I could have fun things to show in addition to simulations that I was going to run and have eventually. So the code that I use called Hammer is really, really fast and allows us to have very high resolution simulations of MHD accretion. And I'm talking, thousands cubed in our resolution, which is the best in the biz, really, because it's GPU accelerated. So all of this is very well and stuff, but the exciting part is that a lot of simulation work that's been done in this field in the past has been in periodic boxes because we haven't had the computational power to do really high resolution global sims like we do now. And so for this project, I wanted to kind of unite that history and legacy of literature on periodic boxes and smaller scale local things with large global simulations by taking a simulation that was run by Matthew and by Bart over the summer, which had a really high numerical resolution, which was like, I think 5,000 by like 2,000 by 2,000 or something similar, which would allow me to take boxes, which were kind of within, less than a scale height of the disk, at various places in the disk and analyze their parameters locally. I could analyze the turbulence, I could get velocity spectra and magnetic energy spectra. I wanted to see kind of ratios of like the guide field into the reconnection field and the current like all of these different parameters so that I can understand kind of where MAD onsets, how it onsets, how the flux is moving through the disk, and whether or not some of these signatures of turbulence might be better indicators even of different accretion states than some of the kind of approximate values that we're using now. Like we'll say, oh, when the magnetic flux reaches this value about, then we call it MAD. But maybe there's something specific about the actuality of the fluid flow. And so I just want to, in my last minute or so, I'll say some of the work that was required of this. Of course, when I'm doing my simulations, they're in some space-time. It is not Cartesian, nothing is Cartesian. It's all in, kind of these cylindrical, coordinates. And so some of the work that I had to do here in order to make this feasible was I had to cut out boxes that were larger than I needed, so that I could reorient them, compute the mean guide field, reorient the boxes along the mean guide field so that I could take spectra, do things like, implement these transforms that would make these things that aren't boxes into boxes, make it Cartesian, reorient things along the right axes and such to even get the initial things that I'm computing on. And so what I ended up being able to do is doing this on a single test case and get some of these scripts going so that I can compute these quantities all over the disk, and hopefully be able to make some conclusions about how these things work. So I think I have all the, during my time at the Flatiron, I got all the raw materials ready and the scripts all tested. And now I have lots of big data to go through with them. So thank you very much.
Thank you so much, Sophia. Really, really great results. Now we have time for a few questions. Vladimir?
Hi, Sophia. Nice talk. So I was wondering about the role of the rotation of the black hole on the dynamo that you're describing. I guess you're probably always considering the case where there was a strongly rotating black hole, and I was wondering if you adjust that, maybe go to a weaker rotation, is that going to affect the dynamo? Do you expect it to affect? Could you learn anything from trying that?
Yeah, I actually modified, I mentioned that today because it's been top of mind when I was looking at the initial conditions of all my simulations. As I was thinking about making this presentation, I saw that every single one, per black hole with a dimensionless spin that was like around 0.93 or something. And so I really do want to modify that to see what the effect is, because it's so clear in all of these simulations that it's not until the magnetic flux gets very close to the black hole that whatever flux it is kind of wins the race, and establishes itself, really gets going, and gets going very suddenly. So again, this could be that, everything is a little more powerful when you get close to the central object. Even just plain old differential rotation is, a pretty sizable effect. But I think that the main way that I can test that is by changing the spin and seeing what happens. And I think that some of the methodologies I developed for my second project will serve me well in my first. Now that I have the toolbox in order to analyze things more locally, I can take, hopefully, a larger, higher resolution simulation of my dynamo stuff and start cutting boxes very near to the black hole. Or actually, in this case, I think it might be better to do shells, kind of like spherical shells here to analyze these quantities. But yeah, it seems like something that's a little more localized, so I can apply some of these new methodologies I've made.
I'll skip this introductory slide. You all know who I am now by now. So over at UT Austin, what I'm doing is actually using near-infrared precision radio velocities to search for giant planets around young sun-like stars. I hope the visual helps that statement a little bit more. So in this middle plot here, what I'm actually doing over for my PhD thesis is conducting a blind search of these giant planets around young sun-like stars using the Habitable Zone Planet Finder spectrograph, which is a very high precision spectrograph that's fiber fed, temperature stabilized, operating in a wavelength range of about roughly 800 to 1300 nanometers. And it's located at the Hobby-Eberle telescope, which is a 10-meter photon power, photon collecting machine. And so we can get exquisite precision on the kind of spectra that we're looking at of these young stars, to hopefully extract some of this information out and detect and characterize these giant planets. And as the survey's been running, I have a couple years worth of data on several, quite a bit of targets actually. One of the problems that I'm encountering is that it's actually really hard to observe young stars, because young stars are extremely magnetically active and they exhibit very strong quasi-periodic RV variability that ends up being very difficult to model. So what I'm showing here is actual data from my survey. For those of you in the audience who don't really do planet work, who don't really do radial velocity work, you can see that the full spread of this goes from negative 500 meters per second to 500 meters per second. So the RMS is something like 250 meters per second. And that kind of spread or scatter within typical RV measurements typically corresponds to the signal that you might see from the biggest, most close-in planets, so the easiest to detect planets out there, hot Jupiters, at about roughly 250 meters per second. And so when I look at this plot, I'm kind of freaked out, a little bit spooked, because if there was no activity signatures, right, if there were no non-dynamically induced variability, then what you do is you take these data points, you shove it through a Lom's-Cargo periodigram, and you try to look for periodic signatures that hopefully corresponds to a planet. But the reason why this variability is really, really difficult is that when you do that and you look at your periodogram or the results of your periodogram, you might see a confluence or a florus of potential signatures that might correspond to one or multiple planets, but it also might just be noise, astrophysical noise. And that's really scary if you're trying to do what I'm trying to do, which is look for these giant planets around young stars. And so I thought really hard about all of this and came to the conclusion that you can't just have exquisite RV precision. What you really need to do is have a robust method to look at your data and really analyze it. And that's why we're revisiting now the tagline of this talk, a Gaussian process framework for hopefully predicting stellar activity signals that I might see in my RV data, and hopefully using this framework to model out and ultimately model out the stellar activity and ultimately boost the detection significance of the planets in my data or in my survey. Gaussian processes, or GPs in general, are these predictive models that actually parameterize the correlation between data points of your observations. So instead of writing down some really gnarly, complex expression for the kind of model that you'd expect stellar activity to follow, especially in the case that we don't really fully understand what's driving all of that. What GPs do is that they have some predictive model or generative model of your observations, and they assume that your observations essentially go as a multivariate Gaussian, which are distributed with some kind of mean model. In many cases, it's a zero model, so it's kind of flat, or in the case that I really care about, some deterministic model, such as a Keplerian signal in your data. And the correlations between your data points or between pairs of data points are going to be described by this covariance matrix, which essentially describes the relationship between how far apart and how close together these data points, or you expect these data points to be. And Gaussian processes have been used very successfully to model stellar variability seen in time series data, such as photometry. So what I'm showing here is a light curve from the Kepler Space Telescope of Kepler 78 from our own Sam Grunblatt and his team back in 2015. I made sure Sam's in the audience, so shout out to Sam. And you can do the same actually in your RV data. Here I'm showing the RV data they collected from Keck High-Res and Harps North, both very high precision instruments. And in these cases, what they're doing is serially training the Gaussian process on the light curve on the photometry, constraining many of the parameters in the activity model in your GP using that light curve data, and then also doing the same in your RV data. And what these models typically assume is that the activity signatures that you see both in the photometry and the RVs share very similar characteristic features. This comes from this very basic assumption that activity-driven modulation that you see typically comes from, at least in very young systems, star spot dominated activity, which is correlated in time. And because of this relationship, what people typically assume is that it's the activity signatures that are imprinted in your observations should typically be the same, both in photometry and RVs. And this is a relatively flexible model, and people have done it again to great success. But the community, of course, is ever driving forward. And even in our cases here with Megan and Dan, what we've seen is that this assumption might not fully hold true, that the characteristic features between the activity models that is latent in the photometry, as well as the RVs, are actually driven by different mechanisms and ultimately manifest in different ways. And so you want to think about this in a slightly more flexible context, such that the activity models aren't purely constrained by your light curve or by the RVs, and extract as much information as you can from both without being fully constrained. So what we're doing here at the CCA, what I'm doing with Megan and Dan, is creating a model where we think of our multiple time series, so photometry or RVs, as linear combinations of two latent Gaussian processes and their derivatives. So let's assume that there's two stochastic processes that we can observe or observe parts of, some FT or G of T, and their derivatives, which we can figure out, F dot and G dot. And what we can do is then set some kind of linear combination. This is essentially, just summing up different amplitudes of these combinations of the processes and the derivatives, like so, in order to model out what our flux and RV looks like. And what this essentially translates to is some covariance matrix, some 2x2 covariance matrix that describes all of the data that you're observing of T of F and TRV. This covariance matrix is what essentially describes the relationship between all of our time series and what's really important. So if you look at the diagonal blocks of our covariance matrix, these are essentially the variances of both your flux data and your RV data. So this essentially tells us, the scatter about those data, those observations. But what's really, really cool is the off-diagonal elements of this covariance matrix, because this then tells us the relationship between your light curve or your RV. This is where we're driving a lot of our power. So before, like I said, what you would do is serially train your GPs on your light curve, and then you would do again on the RVs and grab that information to constrain your activity model. But now that the constraints that we have on our activity model, our GPs, is latent and is well described by the covariance elements here, such that we're no longer constrained in time. Like I said before, the activity can evolve over time, and the mechanisms that drive both the photometry and RVs might actually be different, and they might be different across time scales. And so you're no longer constrained as much. You're much more flexible now. And to my knowledge, and to all of the experts that I've talked to, i.e. Dan and Megan, no one has ever really done this. And so I think we're pushing a little bit forward in this regard. But we want to test to see if our basic assumptions and our understanding of these models actually works. So I've been able to talk to Rodrigo Luger, and using his StarA package, what we can do is simulate emergent and decaying star spots on the surface of a stellar surface map. And then using StarA, calculate that effect of those emerging and decaying star spots, their evolution across time, and propagate that into some synthetic photometry and radial velocity curves. Here, oh great, the video works. You can see across a time period of 20 days, how the spots emerging and decaying here on the right translates, flagging a bit, translates to your observed flux. And so I think this mimics very well what actual data looks like. We can go a little bit step further. So what I'm showing now is a time baseline of about 90 days, both in the light curve on the top and the radial velocity on the bottom. And the light curve, both of these time series, synthetic time series observations is happening at a cadence of around 30 minutes for a total baseline of 90 days, which corresponds roughly to the Kepler telescope, 1/4 of the Kepler telescope observation. And so we can simulate essentially what real data might look like, at least for the light curve. On the bottom, the RV curve is unrealistically high cadence. You won't actually get RV observations 30 minutes at a time for 90 days straight. That just doesn't have, that's not how that works, at least not ground-based observations. But one can dream. But using this extremely high cadence, high fidelity, true synthetic observations, and then adding some noise here so you can see the black dots like that, what we can do is train our model on different segments of it at different cadences, and then see if we can reliably produce or predict what our RV is doing, RV data is actually doing on the back end. And over the course of 4.5 months, after much work and quite a bit of help, I've been able to implement our latent GP model such that it can actually do a good job of predicting what the RVs are doing, even with a very sparse training set. So this is the same data actually, as I showed in the last plot, or in the last slide. Now on the top panel is just a zoomed in version of roughly 10 to 50 days of the previous plot. And I'm using the full data set shown here. So every single data point. And then on the bottom, again, the RV curve, again, this time a different subset of that time axis. So 15 to maybe 35 days. I'm showing all the black dots just for cross-validation to check our models. But what we're using to train the GPs is actually the yellow stars. So I'm only using a handful of yellow stars randomly indexed to simulate what true RV cadence is, 1 or 2 every couple of days. And then using that much more sparse RV index to train our GP model. And then I plot the map solution of our GP model in blue here, solid blue, and the 1 sigma contour lines. And then what I'm trying to demonstrate or show here is that even with this sparsely sampled time observational cadence in the yellow stars, our model is reliably producing the general shape of our synthetic data that mimics activity. And so we're doing a good job of predicting what activity is supposed to do, which is really, really exciting. And one of the primary goals of the project in general, understanding the underlying activity signatures that we see in our time series data, if you have photometry and RVs. But if you remember, if you go back to the original goal, what we wanted to do is find planets, right? And so what I've done now is injected a very simple planetary toy model, and I'm doing the exact same thing. Data shown, light curve data shown on the top panel, same cadence roughly, or same baseline roughly. And the RV data is the same. The synthetic RV data is also the same here in the bottom 3 panels, but now I've injected some planet signal as demonstrated on the very bottom panel. And then the activity signature in the middle and the total RV model in this second plot here. And so simultaneously modeling or fitting for the activity signature and the planetary signature, what we can do is reliably recover, if you increase the cadence very well, asterisk, reliably recover this very simple planetary signal, as well as simultaneously predicting what's happening to the activity behind the scenes to create this extremely exquisite total RV model that predicts our data very, very well. So this is super exciting. And so I'll just summarize really quickly what we're doing, just developing a GP method that models these star spot contributed stellar activity signals in time series data. And in the future work, what I'm going to do is hopefully apply this framework to my own PRV survey to increase my sensitivity to giant planets around young active stars. And that's why it's really exciting, since I can that last plot demonstrates some proof of concept of that. And I'll take your questions now. Thank you.
Hi. No, thanks for the really clear talk. I'm wondering if you have a sense of like how many systems will have enough signal to noise that you think you'll be able to kind of take this kind of approach with it? Is this something where there's just gazillions of them, or is this something where you really need to get this to work for like 10 good targets?
Yeah, that's an excellent question. And so I think in my survey alone, I would personally use this for all my targets, and I have, N of like 100. The parameter space that we're attacking or want to attack is this young active region, because the amplitudes of those modulations are on the scale of tens to higher, tens to hundreds of meters per second. You need the giant planet amplitudes in there. Like I wouldn't not be comfortable saying you're going to find lower mass Earth-sized planets around these very active stars using this kind of technique, not at least robustly. I would say like most giant planets hopefully would be able to be detected, and that's off the top of my head. I don't know, maybe someone else, hundreds of systems. Maybe there's even more, and we just don't know it. The occurrence rate at much older ages is very low because high, very disruptive migration pathways are destroying all of them. So there might be even more, an order of magnitude more, but there is quite a few.
Yeah, thanks for this great talk, Kwang. I just had a question if you've thought about how your sensitivity might improve at different time scales. So like if there's certain planetary orbits that you'd be particularly sensitive to or not sensitive to because of like the beat frequency, or how that relates to the stellar activity timescales.
I haven't thought too much about beat frequency things, but I have thought about if we're just very unlucky and the stellar activity, like rotation period of the star and that activity correlates, and then you also have a planet on the same exact period. Lily Zhao, who I don't know if she's still on the talk, might have a lot more thoughts and feelings about this in terms of periodograms and separating activity signals and planet signals. I think for the most part, even if you're on the same period, if the amplitude of the planet is higher, and how much higher, I'm not quite sure. If your amplitude is higher than the activity signal, you'll still be able to recover. But I haven't done fully, even toy tests to see if that is that big of an issue. I mean, it obviously is. I wouldn't have a good guess for it until I play around with my own data.
Yeah, then I'll ask a question. So very interesting result. I was wondering if you think it would be useful to add some extra information. So right now you have a light curve and you have a radial velocity measurement. And some of the variability that you observe is produced by different type of activity at the stellar surface. So I was wondering if including things like H-alpha emission to your data set could help you to disentangle the correlation between variability in the light and variability in the radial velocity measurements.
Yeah, that's a very excellent question. And so some of the work that's been done on this side of the thing, on using Gaussian process to model activity, uses those activity indicators such as BIS, the CCF, bisector span index, and whatnot. Those models typically use one latent Gaussian process. And so just to explain a little bit more in detail about what we're doing, the reason we have these two is because the light curve and the radial velocities are going to be very different in terms of each other. The spectral information on the RVs and the flux information on the photometry might very much so be different. If you have something like H-alpha emission, you have the spectral information that might be inherent in the radial velocities already, but as you mentioned, it could be probing a different part of the surface of the star itself. My assumption is that, and people can feel free to chime in, my assumption is that more information is good, because you'll never, well, maybe not never, my naive assumption is that you won't hurt your model if you add in more time series information, so more ancillary information. But then you run into this very complicated issue of like scaling all of your parameters. Like you already saw, my delta F and delta RV is equal to some, A plus B plus C plus D versions of these two latent processes and time derivatives. And many arguments can be made to simplify all of this. The reason why we focus primarily on photometry and radial velocities is going back to that, you're already doing a very good job of trying to get as much parameter space of information from the available observations that you have, while at the same time limiting your model and your different inputs. I would be very interested in looking at it. I do not think you're adding that much more information.
Super great talk. So I have two related questions. It's super awesome that it works for individual systems, but I'm curious, like how much you had to tune or constrain the hyperpriors on the GP parameters, and whether you would then do much better at predicting the individual system, GP properties if you then like do all of your 100 systems together in a hierarchical sense.
Ah, I see what you're saying. Yeah, so for your first question, do you mean like, did I bound the, the parameter space for the hyperparameters of the GP? No, I did not bound. There was no, I just kind of left it as it is. And it did a good job of optimizing very well. I think it's not too hard of a thing. GP optimization scales as n cubed because of the way you do all of that math. But I did for a small section. I think bounding will help for sure. Bounding will help. So I played around with this very simple toy model, and like if you decrease the cadence of the RVs that you're observing to the minimum that I showed in the other example, then you start not recovering the planet. But if you bound it, then you start recovering the planet again. And so to that end, to your second question, the hierarchical modeling will definitely, I'm a big fan of hierarchical modeling, population synthesis, but I don't know, because right now what we're looking at, depending on the kernel choice that you use, the kernel hyperparameters, constraining that and then looking at the the population posteriors is most informative if you have some physically intuitive kernel, right? I think that's tough. If, for example, my target of like 100 systems or whatever are these young, so the bin is like kind of tight, but not as tight as I think you could get or should get when you're doing this population. So if you had one specific spectral type or one, solar mass range, if you have one specific effective temperature range and all of that, then I think you can get a lot of information in. But if you just threw an ensemble of 1,000, I don't think you'll get too informative.
Thanks.